There we go. All right, chemistry 3101, 3111. My goodness gracious. There you go. I didn't even have the wrong class. All right. So chemistry 3111. We said we were going to start today by looking at question 20.46. And 20.46 is just give us the major product. So all we're looking for is the major product. So this is kind of just, do you know the reactions from the chapter? So the first one is taking a carboxylic acid, and this is a brand new reaction in this chapter. First, we're going to treat it with excess lithium aluminum hydride. If you want to write LAH, remember that lithium aluminum hydride is the same thing as LAH. It's just the acronym for it. So we use excess LAH followed by treatment with hydronium. I would also accept water. Well, that does a complete reduction all the way down to an alcohol. And so that's what we end up with in this case is we end up with a primary alcohol. So let me just sketch that out here. So if we take this, and I'll try to be as neat as I can here. So let's count our carbons carefully. So we have this carbon, and you can see that that's the one that had the carboxyl attached to it. And so now it's just going to have an alcohol attached to it. So we'll scribble in the alcohol just like that. All right, there we go. First one done. All right, next one is where we're taking the exact same compound. So we're going to take the exact same compound. Sorry, I'm having a problem with my Microsoft Teams. Just bear with me. There we go. We're taking the exact same compound, and we're going to treat it with thionyl chloride. In the first step, SOCl2. And then in the next step, we're treating it with excess. This is called dimethylamine. So you could imagine two methyl groups, and then it's a secondary amine. Well, after the first step, right, thionyl chloride is going to convert the carboxylic acid into an acid chloride. And then I went over the mechanism of the nucleophilic attack and the proton transfer that occurs at the end to make the neutral amide. And so after the second step, after step 2, we're going to end up with an amide, and it's a tertiary amide in this case. So we have our carbonyl, that doesn't change. But now instead of this oxygen, we're attached directly to the nitrogen, and we have our two methyl groups. All right, so instead of writing CH3, I'm just going to put the two methyls as a bond line structure like that. The next one is kind of a one-off reaction. I told you don't have to know. You do not have to memorize the mechanism of this reaction. So let me just see if I can paste this guy in here, and I'll just alter it. So we're starting it with this primary amide, right? And then we're just going to treat that with thionyl chloride. So SOCl2, SOCl2. And again, I told you that you don't have to know the mechanism of this reaction, but what it does is it takes the primary amide, so it takes this primary amide, and it converts it to a nitrile. So we end up with a nitrile. So let's count our carbons carefully. We have our tert-butyl group, we have a methylene, and then we have this carbon and this nitrogen. That's where the nitrile group is going to be formed. And so we're going to have CN like that. That's our nitrile group. If you chose to write the whole, every bond in like that, that's totally fine too, but you can use the condensed structure as well. So I think, be very careful on counting your carbons in these kinds of questions and this kind of synthesis. So let's take a look at the next one. So we're starting off with an ester. All right, so we're starting off with the ester. So this is D. So let me just copy and paste that same structure, and I'll just alter it again. So this is D. So I'll switch that from a carboxylic acid into a methyl ester like that. And in the first step, we're going to treat it with aqueous acid. So that's the first step. And then in the second step, we're going to treat it with acetyl chloride. So they use a condensed structure like this, CH3COCl, but you guys know that that is the same thing as this, okay? It's just acetyl chloride, and we talked about that compound. And then we're going to mix that with pyridine, which is our base. And so after the first step, after the hydrolysis, right, this is just the hydrolysis of an ester in acid. And so what we're going to end up in the first step is, come on, there we go. So if I just take this compound and I turn it into blue, there you go. That's what we get after the first step. We just hydrolyze to the carboxylic acid. So then in the second step, we react the carboxylic acid with the acid chloride. When we treat that with the acid chloride, we form an anhydride. So what's our anhydride going to look like? Let's see. It's going to look like this. So we're going to have our carboxylic acid. I'm just going to modify it here. So we're going to erase this hydrogen, and we're going to have our acetyl group on this oxygen. So we end up with an unsymmetrical anhydride in this case. All right. Again, stop me if you have any questions. The next one I would say is kind of a quick one as well. So this is E, 20.46E. So let me just scribble that down here, 20.46E. We're starting out with a different ester. So this is methyl benzoate. You can practice your ester nomenclature along the way. So if we have methyl benzoate, and we're just treating this with diisobutyl aluminum hydride, diisobutyl aluminum hydride, followed by treatment with aqueous acid. Well, that is just going to reduce the carboxylic acid down to an aldehyde, okay? So we take the ester and we reduce it down to an aldehyde. So take our ester and we reduce it down to an aldehyde using diisobutyl aluminum hydride. All right. And F, we're starting with phenol. So this is 20.46F. We're starting with phenol. This compound here, which we've seen a million times in this class. And then we're going to treat it with acetic anhydride. So remember, acetic anhydride is a reagent, okay? You can treat it as a reagent. And what it does is it adds an acetyl group onto your oxygen. So that's all we're going to do is we're going to draw the compound. Here's the oxygen of our phenol, and then we just put an acetyl group on it like that, and we're done. Now, in this case, we're also going to end up with acetic acid as a byproduct. So we're going to end up with both of these. But again, the major product, the one that we're most concerned with, is going to be the new ester that we're going to form. So this would be called phenylacetate, would be the name of this ester. All right, let's try the next one, which I know everybody would get. Students are usually very good at these reactions where you have an acid chloride and some kind of amine. I'm just going to write pH instead of the whole aromatic ring. So we're starting it with this this amine. This is called diphenylamine. I know we haven't covered amine nomenclature, but I'm pretty sure you guys can figure out where that name comes from. So diphenylamine, two phenols, and it's an amine. It's a secondary amine. And we're treating that with acetyl chloride or acetyl chloride. Either one is fine. So with acetyl chloride, and of course we're using pyridine as a base. And what we're going to end up with in this case is going to be a tertiary amide. So we have our nitrogen and we have our two phenols like this. So you would call this NN-diphenyl acetamide or NN-diphenyl ethanamide. Either one would be a proper name for this compound. All right, the last one involves a cyclic ester. So 20.46H involves a cyclic ester. And hopefully you remember the name of a cyclic ester. Does anybody remember what a cyclic ester, the proper term is for a cyclic ester? Starts with the letter L. Anybody remember that one? So if we have an ester in a ring, it's called a, no, it's called a lactone. A lactone is an ester in a ring. So a lactone is an ester in a ring. So all we're doing here is we're hydrolyzing an ester in an acid. Okay. So what we're going to do is we're going to cut the bond here, and we're going to end up with a carboxylic acid on one end, and then we're going to end up with the alcohol on the other end like that. So let's draw the product. So we end up with something that looks like this, where we have our carboxyl group here, and then we have our alcohol like that. So you'd call this orthohydroxybenzoic acid. It would be for that compound. Everybody with me on those reactions? Any questions about those ones? Anything earth-shattering in those? No? Okay. Everybody good on that? Okay, awesome, awesome. Let's try something a little more challenging. So I'm not saying these aren't challenging. There's a lot of information in here, right? We covered a lot of information in chapter 20.
It's too basic.
Sorry, which one? Did you have a question? Tanika?
Oh, sorry. No, sorry.
Okay, okay. All right. So there you go. So that's, a little bit of, a nutshell of a few of the reactions from the chapter. But now what we're going to do is we're going to take it and we're going to expand on this in the next question, which is 20.51. Okay, this one I worked out in detail before I came to class. I didn't look at the solutions manual, but I probably solved them the same way he did. And if I don't, well, let me know. And so with the first one, we're trying to do is take this compound. This is just bromocyclohexane, and then we're going to try to make this ester from it. Okay, so we're going to try to make this ethyl ester. All right. So I think the best way to do this would be to a Fischer esterification. So if we had the cyclohexane carboxylic acid, meaning if we had this compound, so cyclohexane, carboxylic acid, right, then we can just do a Fischer esterification with a catalytic amount of acid, ethanol, and then of course the removal of water, and that's going to give us our final product. So then the question becomes, how do I get from here to here? Did anybody come up with a strategy for this one? How to get from the the bromocyclohexane to the cyclohexane carboxylic acid? Where I have the question mark. Does anybody have a strategy for that one? There's a really important reaction that we've covered this semester that I think would be the best option to make that carboxylic acid. Anybody? No? Okay. Well, I think the best way to do it would be using a Grignard. Okay, if we use a Grignard, all we have to do is we just take our alkyl halide. Oops. We'll treat it with, in step 1, we'll treat it with magnesium. That will create the nucleophile, the Grignard reagent. In step 2, we treat it with CO2. That'll make a carboxylate. In step 3, we treat it with aqueous acid, and that will protonate it, and that will give us the cyclohexane carboxylic acid, just like that. So now all we have to do is a Fischer esterification. So we're going to treat it with a catalytic amount of acid, ethanol, and we'll write here removal of water, and that's going to give us our ester. So all we're doing here is a Grignard. This is a Grignard synthesis of a carboxylic acid. And this reaction here, this is the Fischer esterification, one of the most important reactions in all of organic chemistry. And I told you, you really have to know this mechanism. We did the hydrolysis of an ester in aqueous acid, but you also have to know how to draw the formation of an ester from a carboxylic acid. So very important chemistry there. All right, let's move on to B. So this is 20.51B. 20.51B, like this. This one's kind of an interesting one. There's more than one way to solve this one probably. But so I'm taking this secondary alcohol and we want to convert it to a ketone. All right. So the way that I think about making a ketone, if you already have like this part of the compound is already cut, you can kind of see it. It's here, right? So if you want to do that, I always think the best way to do it is using a cuprate. So if we had a cuprate, we could add to the aldehyde one time. That's one way of doing it. Another way to do it would be to use a Grignard. So I'd say either one is fine for that one. Yeah, I'd say either way is fine. You could either use the acid chloride or you could use an aldehyde. So let me show you how to do it using an aldehyde. So the idea is this: if we have the aldehyde, so if we oxidize the primary alcohol using PCC to give us an aldehyde like this, a cyclohexane carbaldehyde, then all we have to do is treat it with ethyl magnesium bromide, followed by H3O plus or H2O, either one is fine, and that is going to give us this compound. So we, come on, Mr. Dion, we end up with this compound, come on, iPad, where we have our secondary alcohol, and then all we have to do is oxidize it, and you can literally choose any oxidizing agent that we have learned. It's going to convert the secondary alcohol into a ketone. I'll just use Jones reagent, sodium dichromate, sulfuric acid, and water, just because it's really strong and it would oxidize it completely. There is another way to do this one though, okay? And that was what I was kind of getting at was, so there's nothing wrong with this route at all, but we could say here alternate would be to make this compound from an acid chloride. So if we had an acid chloride, then we could use a cuprate. We could use a cuprate, which is only going to add once to that acid chloride. And so to make the acid chloride, it's actually pretty quick. Okay, all you have to do is take the primary alcohol and oxidize it using the Jones reagent. So if I just say here, I'm trying to make this compound. Let me just draw it here again. Okay, this is our target. What we're going to do is we're going to oxidize this completely using sodium dichromate, sulfuric acid, and water. And that's going to give us the carboxylic acid. Then we can use thionyl chloride to get the acid chloride, so SOCl2, like that. So that's going to give us our acid chloride, like that. Not my best work. And so from here, you would use the cuprate. So for the cuprate, you would just use lithium diethyl cuprate is what you would use, and that's only going to add one. So there's nothing wrong with either of them. Let's see, the one on the top is 1, 2, 3, 4 steps. The one on the bottom is 1, 2, 3, 4 steps. So I would say they're both fine. Okay, there's nothing wrong with either of them. They're both perfectly reasonable. But there you go. And that's something that you're going to find as you move through the content, that you're going to find more and more questions where you have other or different ways of solving them. Let's try one that's, I would say, is a little more challenging. I've asked this question on a quiz years ago. This is 20.51. This is question C, okay, where we're starting out with bromocyclohexane. So let me make sure. Do I have the right one here? Yeah. So we're starting out with bromocyclohexane. And we want to make this really cool amide. So we have something that looks like this. Then we have a methyl group on here. And then we have an acetyl group on here. It's actually not that abundantly clear how to make a compound like this. This is one where I say that retrosynthesis is going to be, is going to be your friend. Unless you're really good at forward thinking, probably going backwards is the easiest way to do this. And I'm using the word easy very, very, I'm really taking risks using that word, I guess. Anyhow, so what if we do a first retrosynthesis and we say, let's just think about the acetyl group, okay? If I just think about the acetyl group, then that means I have to have this compound, right? Because I could add the acetyl group using acetic anhydride, that will work, or I could use acetyl chloride, that works too. Either one is fine. But then to make this compound, it's not that abundantly clear because this is a secondary amine. And we didn't talk a lot about amine synthesis, like how do you make an amine? But if you are very astute, and I know you all are, you probably remember that we could make this from the amide, right? If we have the amide, we can reduce it to the amine using lithium aluminum hydride, okay? Now it's starting to get more reasonable because from this, we can use Grignard chemistry to make a carboxylic acid, then we could convert it into an acid chloride, and then we could make this secondary amide by using methylamine, okay, to give us that compound. So that kind of helps piece the synthesis together in a way. So if you're unclear about what I mean, what I'm getting at is this. So look, I'm going to put a few steps here. I'm going to put step 1, magnesium, right? That makes your Grignard reagent. Step 2, CO2 is your electrophile. Step 3, H3O plus adds the proton, so you get the carboxylic acid. So after this point, you get the carboxylic acid, and then you're going to treat that with thionyl chloride to get the acid chloride. Now that we've got the acid chloride, you can see that we can make the amine with relative ease, okay? So we're going to treat it with CH3 and H2. Now, of course, we're going to need an excess of that because you need a second equivalent to do the deprotonation. But that is going to give us the compound that I have written in red, okay? So what I'm going to do is I'm just going to save a little bit of real estate for myself here. And I'm just going to copy and paste this molecule. I'll bring it down here and I'll change the color like that. Okay. So now we have this compound. Now what we have to do is we have to reduce it. Okay. So we're going to reduce that to the secondary amine. How do we reduce it? We use lithium aluminum hydride. So we're going to use, we'll put here step 1 is going to be excess lithium aluminum hydride. Step 2 is hydronium, like that. And that is going to give me the amine. So I have the amine like this, like that. And then the last step is just to add the acetyl group. You could choose acetic anhydride. That will totally work. Or you could use acetyl chloride. Either one is totally fine. I'm going to use acetyl chloride. And you would only need half an equivalent of that because you need twice as much of this as you do of this, right? Because the second equivalent is going to do the deprotonation. I'm just going to put 0.5 equivalents. If you don't put that in your work, if I gave you a paper quiz on this, it wouldn't be the end of the world. And so after all that, we're going to end up with our product. So there you have it, folks. So how many total steps is this? 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 steps. That's not a joke. You know? 8-step synthesis is a pretty complex synthesis. All right, give me a thumbs up if you're with me on the rationale for that one. Any questions about that one? I think that question is rather challenging. Does anybody follow me on that question? Okay, cool. All right, cool. Let's see here. Blah, 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 blah. Let's try another one that's a little more straightforward, maybe. And this is 20.51D. So we're starting out with this primary alkyl halide, and then we're going to convert it into this ketone. Let's draw our ketone like this. So if we count the carbon starting on the left, and this is not for nomenclature purposes, 1, 2, 3, 4, 1, 2, 3, 4. So you see that we're adding this portion here. So there's actually a few ways you could do this thing, okay? You could do a Grignard. I think that's a really good way of doing it. Using a Grignard and then just oxidizing like that. That would totally work. You could, what else? You could displace it with a nitrile, with a cyanide. That would work. And then use a Grignard on that and then hydrolyze that. That would totally work as well. So I don't see anything wrong with either of those. But let's say we try to make it via the Grignard. We'll do it 2 ways, okay? If we try to make it via the Grignard method, what you would do first is you would treat this with magnesium to make your Grignard, and then the electrophile that I would choose would be acetaldehyde, okay? Because then it's going to do the nucleophilic attack at this carbon, and you're going to add these 2 carbons, right? Because you need to add carbons 5 and 6 here, if you want to call them that. So we'll call this 5 and 6, like that. So after proton transfer with H3O plus, what are you going to end up with? So we have 1, 2, 3, 4, then 5, 6, and we would have the secondary alcohol like that. So that means in the next step, all we have to do is oxidize that using PCC. There's nothing wrong with doing it that way. I saw that in my notes from a couple of years ago that I had a problem similar to this, and I took a much longer route. So I think this is a good way of doing it. However, there is an alternate way. So alternate, and I've asked a question similar to this on a quiz before, and most students didn't come up with a simplified or using an imide or a shift base, but I'll show you quickly what I mean by that. So if I just copy everything down, so we'll change the color to blue. Okay, so in this case, what we would do is this. So let me just bring it down here. Just bear with me. Let's move it all the way down here. Okay, so what we're going to do, and this is, again, this is D, okay? What we're going to do is we're going to hit this with cyanide. So if we use sodium cyanide. So cyanide is a good nucleophile. It's a weak base, and that's going to do an SN2 reaction. And we're going to end up with the nitrile. So we end up with this, and then count your carbons carefully. So we have this, C triple bond N, like that. Okay, so there's our nitrile. My bond angle is a little squirrely the way I drew it. It should be like this to be more proper, but you get the idea. Okay, so now this is a reaction that you might not think of a lot, but now we just have to add this methyl group here. And so we can use methyl magnesium bromide in the first step, okay? And if you remember, I'll just draw the intermediate that you're going to get, which is going to look like this. You're going to have something that looks like this, okay, where you have a negative charge here, and then here's your methyl group that you added on. And so in the last step, when you do the proton transfer with H3O plus, what that's going to do is that's going to do the proton transfer to make the imine, right? So if I treat it with H3O plus, I am going to end up with the imine as an intermediate, okay? But remember, if you put an imine in aqueous acid, it's going to hydrolyze it all the way to the carbonyl compound. So that's another way of doing the exact same problem. And I'm sure that some of you came up with other ideas than what I had. I mean, you could use formaldehyde and then make an acid chloride or something, and then use a Gilman reagent or a cuprate. That would totally work too. All right, let's keep going. Let's see, let's check the time. Good. All right, let's do a few more. So it's 20.51. So we've covered all those. Now I wanted to take a look at 20.69. Just scroll down here. So 20.69. I went through all of these ones too. So 20.69. I think we're running out of Taylor Swift blank space out there. So let's just delete some of our old work. Nope. There we go. Just bear with me. I'm just deleting this so I can have some room to work here. All right, so let's go back to the top. So this is question 20.69. And these are some challenging synthesis problems in this one. So the first one is we want to take benzoic acid, which is this compound that you all know very well, and we want to make an acetal. So we want to make an acetal like this. So here's our acetal. So how are we going to do that? Well, I think the best way to tackle this one is to use a little bit of retrosynthesis. So what we're going to do is we're going to say, okay, well, the way to make the acetal is from the ketone. So if I had this ketone, right, all I'd have to do is treat it with ethylene glycol at catalytic amount of acid. And yeah, and removal of water, and that would give me the acetal. And I'd say, yep, that sounds good to me. And so what do we need to do first is we need to make this ketone. And I would say the best way to do that would be from the acid chloride, right? If we had the acid chloride, then all we have to do is do a Gilman reagent, okay? Or a cuprate, right? And the cuprate is going to add only once to that acid chloride, and it's going to give us the final product. So that kind of answers the question pretty quickly. So the first step is going to be thionyl chloride to make the acid chloride. So that gives us the acid chloride. The next step is going to be the cuprate, which is going to be lithium diethyl cuprate. And that's going to give us our ketone, which is going to be this compound here. And then to make the acetal, we're going to treat it with ethylene glycol, catalytic amount of acid, and we'll write here minus H2O. And that gives us our acetal like that. Okay, next one involves the shift base. When was the last time you thought about a shift base? I don't know, a couple of months ago. So this is 20.69b. So we're taking this primary amide. So this is cyclohexane carboxamide. We looked at this compound when we talked about nomenclature, and we want to make this imine. Remember that the old term for an imine is a shift base. So we want to make this imine, and we know that if we want to make an imine, we need to start out with the carbonyl compound. So we're going to need cyclohexane carbaldehyde. Okay, we also tried to name that compound, or we did name that compound earlier on, like that. Okay, so now we know that we could make the aldehyde from the carboxylic acid, and we know we can hydrolyze the amide down to a carboxylic acid. So if we just take this and treat it with aqueous acid, that's going to give us the carboxylic acid. And if we have the carboxylic acid, again, we could reduce that with lithium aluminum hydride, and then we could oxidize it back up using PCC or a SWERN. So that's one way. So I'll just write this down here. So just bear with me. So I'm going to put LAH in the first step. That would give you the alcohol. Second step is H3O plus to do the proton transfer. And then the third step would be PCC. And that would give me, there's no debate, that's going to give you the aldehyde. However, there is another way. You could also treat it with, so I'm going to put here, or you could treat it with thionyl chloride to make the acid chloride. And then you could reduce that using lithium tri-T-butoxy aluminum hydride. So lithium tri-T-butoxy aluminum hydride, like that. Either one is totally fine. And then to make the Schiff base, the imine, what do we need? In this case, we would need methylamine, a catalytic amount of acid, and then we always write minus H2O because it's a dehydration reaction. Everybody good with me on these? Any questions about that one? Sorry, I can't see the reaction. Everybody good on that one? Any questions? No? Okay. Well, stop me if you have one. Okay, the next one is a real doozy. This is question 20.69C. I almost always do this question in class with my students. Okay, when I have the class in person, like I will in the fall, I almost always do this question because it will boggle people's minds. And I don't mean that I'm trying to be difficult, but it's just to kind of dredge up a reaction that we don't think about a whole lot. Or, even when the first time I saw this question, I was like, oh yeah, okay, like how would I do this? And the key to this reaction, because you think, well, okay, you can clearly see that if I use a yellow pen here, that this part of the molecule and this part of the molecule are intact. But then if you're like, well, how do I replace an isopropyl group with a dimethylamino group, right? How do I go from this ketone to this amide? And the answer to this one in the retrosynthesis is a Baeyer-Villiger reaction. So the Baeyer-Villiger reaction. If you haven't thought about it, it's time to think about it now, because on this side we have a secondary carbon, and on this side we have a primary. And so if we treat it with a peroxy acid like MCPBA, so let me just scribble that down here. I'll put MCPBA based off of the migratory aptitude. You're going to end up with this ester where the oxygen is going to insert in this side. Now, if you've forgotten the migratory aptitude, okay, which I'll blame you if you did, it goes hydrogen, then tertiary carbon, then a secondary is tied with a phenyl, and then we have a primary, and then we have a methyl is the bottom of the barrel, like that. So since we have a secondary versus a primary, the oxygen inserts here. And then if you're thinking, well, okay, now I can just hydrolyze this, right, with aqueous acid, and that's going to give me the carboxylic acid, and then you're off to the races, right? Because now you can convert that into an acid chloride using thionyl chloride, like this, and then you can see very clearly that all you have to do in the last step is to take dimethylamine, a catalytic amount of acid, and to remove water. So if you need to go back and review the Baeyer-Villiger reaction, it's not a bad idea. I would do that. Okay, I would totally go back and take a look at the Baeyer-Villiger and remember the migratory aptitude, because it can really get you out of a bind in a question like this one. Let's take a look at the next one, a little bit more straightforward. So this is 20.69D. So 20.69D. All we're going to do in this one is we're going to take this methyl ester. So this would be methyl butyrate, and we're going to convert it into a thioacetal. So do I have the right number of carbons? I do. So we're converting it into this thioacetal. And so to make the thioacetal, I'm going to have the aldehyde. So we'll draw the aldehyde like this. Now, if you're saying, well, all I have to do is hydrolyze this to, a carboxylic acid or something, and then reduce it all the way down to an alcohol and then oxidize it back up, I suppose that would work. It might not be the most elegant way of doing it, but I suppose it would work. It wouldn't be unreasonable. But there is a better way, because we said that we can reduce an ester down to an aldehyde, and we can just stop at the aldehyde. Does anybody remember the reagent that we would use to do this? If we want to take an ester and stop at the aldehyde. Take an ester and just stop. Poof, right at the aldehyde. Don't go any further. Kristen, all I can see in the chat is the word nope, but I think that's from like a half an hour ago. So, does anybody have an idea? What about diisobutyl aluminum hydride? Right? If you guys remember, DIBAH. Okay, that's the way that you would reduce it. Reduce it down to the aldehyde. So, first step is going to be diisobutyl aluminum hydride, followed by treatment with hydronium. That's going to give us the aldehyde. And now all we have to do is treat it with the 1,2-ethane dithiol, this compound. We need a catalytic amount of acid, and we remove water, and we're done, just like that. Okay, let's try one more. Let's do one more. Let's do 20.69, and this is E. Gonna do another question that involves an acetal, right? So if we want to take benzoic acid, so this compound, benzoic acid, and we want to make an acetal off of the aromatic ring. So if we want to make something that looks like this, all right. So we want to make an acetal like that, not my best artistry, but there you go. Well, we know that that is going to come from benzaldehyde, so we need to have the aldehyde like this, okay? And then all we'd have to do is treat it with ethylene glycol, catalytic amount of acid, and then we're off to the races. So then the question becomes, well, how do I get from here to here? You know, what's the fastest route? Well, I think the best way to do it is to convert it into an acid chloride and then reduce using lithium tri-T-butoxy aluminum hydride that we saw earlier today. So we're going to treat this with thionyl chloride. That's going to give us the acid chloride. It's going to give us the acid chloride like that. Then if we treat that with lithium tri-butoxy aluminum hydride, so there we go, followed by treatment with water or aqueous acid. I'll put aqueous acid because that's what he has in the textbook. That's going to give us the benzaldehyde. That's going to give us the benzaldehyde. And then to make the acetal, I treat it with ethylene glycol, acid catalyst, and I always write negative H2O. Why? Because I'm losing water in the overall process. And that gives us our acetal. Let's try one more. I guess that's going to, no, we'll try the second to last one. So this is F, 20.69F. This one's kind of an interesting one too. I'll just use phenyl to abbreviate the aromatic ring. So we're starting it with this compound. That's a little prettier. And we're trying to make this carboxylic acid. So we're trying to make this. This is called phenylacetic acid. The name is neither here nor there, but you can see how this is acetic acid, and then you just tack a phenyl onto it, so it's called phenylacetic acid. Anyhow, so if you want to make phenylacetic acid from this starting material, I mean, how are you going to get an oxygen in between this this carbon in red, okay? How are you going to put an oxygen in there? The answer is the Baeyer-Villiger reaction. Again, right? Because if you look at the migratory aptitude that we had written down before, so take this and we'll just copy and paste it. So if we put the migratory aptitude down here, okay, we'll put it right there. If I use MCPBA, or I can just write RCO3H, that's totally fine. Right, on this side, we have tertiary. On this side, we only have primary, so the tertiary is going to win. And so that is going to be a way that we can put the oxygen in there after we do the oxidation. So the first thing we have to do is oxidize to a carbonyl. And so what I'm going to do is I'm going to do it in 2 steps here. I'm going to say step one is PCC. That's going to give me the ketone. And step 2, I treat it with the peroxy acid. That does the Barrett-Villiger reaction, and there you go. Now I have my ester, and now I can hydrolyze that ester. I can hydrolyze it in acid. I can hydrolyze it in base. Either one is fine. I'm going to choose to do it in acid. So maybe I'll put my arrow kind of like this. Okay, something like that. Okay, so I'm just going to use aqueous acid. And you can put heat there if you want to. You don't have to, but that's going to hydrolyze it to the carboxylic acid. All right, I keep lying. Okay, let's try one more. So this is 20.69. And this is the last one in it. This is G. We want to take this lactone, right, this cyclic ketone, and we want to make this acetal. So let's see here. It looks something like this. There's my CHEM dimethyl. Nope. It's going to look more like this, this. There we go. Okay, so I want to make this acetal. So if I count the total number of carbons, I have 1, 2, 3, 4 here. And I have 1, 2, 3, 4 in here. And so in terms of retrosynthesis, what I need to have is this 1, 2, 3, 4. I need to have 1,4-butane diol, and I need to have acetone, this ketone here, and then a catalytic amount of acid and removal of water, and that's going to give me my acetal. So how do I get from here to here? Well, you can see all I have to do is hydrolyze that lactone, and it's going to give me that compound. So if I take this and I treat it with aqueous acid, I'm going to end up with, let's see here. Sorry, did I say aqueous acid? That's not the best idea because that's going to give me a carboxylic acid and an alcohol. I misspoke. The best way to do it is use lithium aluminum hydride. So if I just delete the whole thing. I think somebody's trying to tell me that maybe I should put an end to doing these problems. But let's try to squeeze it in here. So now that I lost all that, so this is 20.69 G. Let's try it again. So we're going to start out with the lactone like this, and we want to make this acetal. Here we go. So what are we going to do first after I misspoke? We're going to use excess lithium aluminum hydride followed by treatment with water or aqueous acid. That's going to give me the diol I want. So I have 1, 2, 3, 4 carbons. So I have 1,4-butane diol. And then to get to the final product, all I have to do is treat it with acetone, a catalytic amount of acid, and removal of water. And bingo, bango, bongo, hot dog, we have a wiener. There you go. That's the whole thing. Just like that. All right.